Hi everyone, my name is Golovnev, and I would like to present our recent result with Sasha Kulikov and Ryan Williams on circuit depth reductions. In this work, we do not prove new circuit lower bounds, but we give a new framework for a new way of proving circuit lower bounds or formula lower bounds. In particular, we'll show that improvements on the currently known pseudo-random objects would lead via our framework to new circuit lower bounds. All right, so the outline of this talk is the following. First, I will introduce the computational models we're going to be working with, the model of Boolean circuits and the model of Boolean formulas. And then I'll present a couple of our circuit depth reductions. And in particular, I'll explain how to use them to prove new circuit lower bounds. Finally, I will show how we achieve similar results for Boolean formulas too. Okay, so Boolean circuits and formulas. Say we want to compute a function from n bits to 1 bit by a straight line program. Straight line program means we run, we evaluate one command after another one without any branchings. We don't have if statements, we don't have loops, no branchings at all. Such a program is called a straight line program, and it can also be always written as a directed acyclic graph, a DAG. And such a DAG is called a circuit. Okay? So formally, we have n inputs, x1, x2, xn. We also have this constants, 0 and 1. In gates, in the nodes of this graph, we compute any function of two Boolean variables. And we do not pose any restrictions on the out degree, on the fan out of the gates. Okay, so this model of computation is called Boolean circuits. And size of a circuit is the number of gates in it. In the 40s, Shannon showed that almost all functions, say a random function with high probability, has a circuit size at least 2 to the n over n. Has exponential circuit size. And in the 50s, Lupanov gave essentially matching upper bound. Every function can be computed by a circuit of size essentially 2 to the n over n. So we know that most of the functions have exponential circuit complexity, but the challenge is to find an explicit hard function. Explicit here means a function from a reasonable complexity class. So we know that most of the functions have exponential complexity, but we don't really need exponential lower bounds. Even if we find a function that cannot be computed by polynomial size circuits, we already prove that P is not equal to NP. If this hard function is from the complexity class NP. So we know that most functions have exponential complexity. We kind of want only super polynomial complexity, but the best what we can prove is just roughly 3n. Even if we consider a much larger class of functions, that e to the np, exponential time with an np oracle. Even there, the best lower bound we can prove, the best circuit lower bound we can prove for such functions is roughly 3n. All right, but we have many candidates for super linear circuit lower bounds. Say we know how to multiply two integers by a circuit of size n log n, and many people conjecture that this should be tight, that we should be able to prove a matching lower bound. We just don't have tools for proving such lower bounds. Same with the discrete Fourier transform. We know how to compute it by a circuit of size n log n, and probably this is optimal, but we don't know how to prove matching lower bound. For many shifts and permutations of the n input bits, we also conjecture superlinear circuit lower bounds. We just don't know how to prove them. Finally, if you pick your favorite NP-hard problem, then most likely it requires circuits of superlinear size. So we have many candidates for superlinear circuit lower bounds. We just don't have tools for proving this. Here's what we can prove though. If your circuit has depth 2, then this is essentially a CNF or DNF, and this is more or less the only circuit model which we understand quite well. Here we know that even the parity function requires circuits of the largest size, of size 2 to the n. So here we're like very good at proving circuit lower bounds. If circuits have depth 3, 4, or any constant z, then still we do know how to prove exponential circuit lower bounds. For circuits of depth 1.9 log n, for where every gate has funding 2, has in degree 2, again, we know functions that cannot be computed by these circuits. But already for depth 2 log n, we know nothing better than a lower bound, that circuit size lower bound of roughly 3n. Okay, so even for the depth 2 log n, nothing non-trivial is known. So natural problem on the frontier right now is to prove a non-trivial, even like linear lower bound for circuits of logarithmic depth. More generally, our goal now is to prove a superlinear circuit lower bound for log depth circuits. Okay, so why can't we prove interesting circuit lower bounds? For proving lower bounds against these unbounded depth circuits, the only known technique is gate elimination. And this technique is just actually an ugly case analysis. We don't want to do this, and moreover, now we know that this technique cannot prove interesting circuit lower bounds. It cannot lead to circuit lower bounds better than, say, 5n. But for log depth circuits, Valence in 1977 gave us a wonderful tool for proving circuit lower bounds. Again, we don't know how to prove such circuit lower bounds, but at least for log depth circuits, we have a non-trivial and interesting way of attacking this problem. So now let me sketch Valence result. Valence says that if you have a function that can be computed by a linear size log depth circuit, then it can also be computed by a depth 3 circuit where the top OR has sub-exponential in degree, 2 to the n over log n. Then we have level of n's, and the bottom ORs have in degree n to the epsilon. Okay, so now if you find the functions that cannot be computed by such a depth 3 circuit, then you also get a superlinear circuit lower bound for log depth circuits. All right. That's a structural result of Valence for log depth circuits. So let me put it in the context. We want to prove a lower bound of 2 to the n over log n for depth 3 circuits, and this would lead to a superlinear lower bound for log depth circuits. The best what we currently can prove is slightly smaller than 2 to the n over log n, but we know really many ways of proving lower bound of 2 to the n to the 1 minus epsilon, so hopefully one day we'll improve it. Also, if the bottom degree was constant rather than n to the epsilon, we could prove even stronger depth 3 lower bounds, 2 to the linear in n. And again, we know several ways of doing this. So we know several ways of proving slightly weaker results, and improvements on them would lead to superlinear circuit lower bounds against log depth circuits via Valence approach. Okay, so the result of Valence takes a log depth circuit and reduces it to depth 3 and says, now prove a lower bound for depth 3 circuits, objects that we understand better, and then we'll transfer this result to log depth circuits. All right, so the proof of Valence, though, it views a circuit as a graph. It never looks at what is computed at any gate of the circuit. And it is known that such graph theoretic results cannot be generalized to circuits of depths larger than log n. Valence approach works really well for log depth circuits, but it probably cannot work for circuits of super logarithmic depth. Our first result is a similar depth reduction, but for circuits of unbounded depth. Unfortunately, currently it only works for circuits of small size, but unbounded depth. All right, let me show you a toy example how such a result for unbounded depths can in principle be proven. That's just a toy example. Say, I want to say that any circuit, unbounded depth circuit of size S, where S, think of it as, I don't know, 3 and 4 and say maybe 3.5 n, can be computed by an OR of exponentially many formulas, each of some small size. Formula is a circuit where out degree of every node is just 1. Okay? Formulas are much easier to work with than circuits. So this result says that you can start with a circuit and rewrite it as an OR of exponentially many, but much simpler things, formulas. In a minute, I will explain you why such a structural result may be of interest, how to use it to prove circuit lower bounds. For now, let's prove this toy lemma. I want to say any circuit of size S can be computed by an OR of in degree 2 to the S over 3 of small formulas. How do I prove it? I look at my circuit of size S. So say this is circuit C of size S. And I find the topologically first gate that has out degree 2. Here it will be, say, this gate G. It has out degree greater than 1. Since this is topologically first gate, it means that whatever G computes is a formula, because all previous gates had out degree 1. So they were computed by formula. G can be computed by formulas, that's important. And now I want to look at two circuits. The first circuit is my original circuit C, where instead of G, I have 0, where G evaluates to 0. If I have 0 here, then I don't really need this gate. I don't need this OR of 0 and something, because the OR of 0 and something is just like the previous gate. I can directly wire the previous gate to 0. And similarly, I don't need this gate because it's XOR of 0 and input. So this is just input. So the circuit C0, where G computes 0, is 3 gates smaller than the circuit C. Similarly, circuit C1, where G computes 1, is smaller by 3 gates as well. I don't need the gate G, and I don't need 2 consecutive gates either. Okay, so I have 2 circuits, C0 and C1, and they both are smaller by 3 gates than the original circuit. Then I say whatever my original circuit computes can be written in the following way. If this gate G is 0, this is my way of saying if in circuits. If G is 0, then I just output what my C0 circuit outputs. Otherwise, if G is 1, then I output what circuit C1 outputs. And size of both of the circuits and size of C1 as well, they're smaller than the size of the original circuit by at least 3 gates. Therefore, some simple inductive argument says that I will eventually rewrite my original circuit C of X as an OR of 2 to the S over 3 small formulas. All right? So this finishes the proof of this lemma. Every circuit of size S can be written as an OR of size 2 to the S over 3 of small formulas. Now, how could we use such a result for circuit lower bounds in principle? Imagine that we had a function f that has small correlation with all small formulas. Small correlation means whatever formula of linear size I take, it correctly computes my function f only the half of the inputs plus some sub-exponentially many inputs. That is, any small formula computes f correctly only at this many inputs, half of the inputs plus 2 to the little of n. It's easy to compute my function correctly on half of the inputs. You just output either 0 or 1. At least one of these functions compute my function f correctly on half of the inputs. But I'm saying that any small formula has small advantage over this. Only 2 to the little of n inputs. All right, if I had such a function f, then I would have a nice circuit lower bound. Indeed, each such formula would only compute f correctly at like 2 to the little of n inputs. So I would have to have s over 3 greater than essentially n minus little of n to compute my function at all 2 to the n points. Or in other words, I would have a circuit lower bound of 3n minus little of n. And we in fact do know functions that have exponentially small correlation with all small formulas. Just the correlation is 2 to the minus epsilon n rather than 2 to the minus n. So they're not strong enough. Moreover, applying Parseval's equation, one can see that the best correlation bound we can hope for is 2 to the minus n over 2. We cannot even hope to get this correlation. All right, but from this you can actually recover circuit lower bound of 1.5, and a simple improvement of the trivial improvement of this argument gives you a circuit lower bound of 2n actually. But this two example demonstrates us how to use such structural results for circuit lower bounds. And it also shows us what we need to improve in this lemma. First of all, if we want to prove circuit lower bounds better than 3n, then we need to improve this constant 3, because currently it can only lead to circuit lower bounds 3n minus little of n. And the second thing, we want to improve these formulas. We see that formulas are not sufficient for proving circuit lower bounds. We want to have something more structured here than just formulas of small size. And in fact, the first result of this paper achieves this. It improves both of these things. First of all, it improves the exponent 3 to 3.9, almost 4, and it also improves the class of formulas to some small CNFs, much more structured class of formulas. So our first structural result says that a circuit of size S can always be computed by a depth 3 circuit where the top in degree is 2 to the s over 3.9. And then we have a small size CNF, not just a formula, but even linear size CNF. Very structured formula. In other words, yeah, we know that a random function, most of the functions cannot be computed by such depth 3 circuits. And it's not hard to see that improvements on the known constructions of dispersers or correlation with polynomials or depth 3 circuits would give lower bounds against this class of circuits, and those were our framework against unbounded depth circuits as well. All right, we also give a similar structural result for linear circuits. We say that improvements on the currently known rigidity lower bounds would give non-trivial circuit lower bounds against unbounded depths linear circuits. But I don't wanna stop on this result now. If you're interested, please take a look at our paper or drop me an email. Okay, and the remaining time, I would like to show how we can do similar depth reductions for formulas, for De Morgan formulas. So recall that the De Morgan formula is a formula where all gates are ANDs, ORs, or NOTs. We don't have, say, parity gates. And since this is a formula, every out degree is exactly 1. Okay? A long, very beautiful line of work shows a formal lower bound of essentially n cubed. And here, our main result gives a framework for proving potentially later a formal lower bound of n to the 4th. Okay? So we say that, first of all, under a conjecture, I will explain what this conjecture in a minute. Under some conjecture, every De Morgan formula of size almost n to the 4th can be approximated by a real sum of sub-exponential size of F2 polynomials of sublinear degree, that is of mods, that is parities, mod 2s, that is parities, of n's of sublinear degree. Once again, every De Morgan formula under some conjecture of size almost n to the 4 can be computed by a real sum of sub-exponential size of F2 polynomials of sublinear degree. All right, so first of all, this theorem currently only holds under some conjecture, but we believe that this conjecture is kind of plausible. And second, in order to get actual De Morgan formal lower bounds, we need functions that cannot be computed by such depth-3 circuits. We know that a random function cannot be computed by such a beast, and we have some partial derandomization results. We know that we know more explicit functions that cannot be computed by weaker versions of these depth-3 circuits. So currently, we're using an unproven conjecture, and we don't yet have a provable function that is a function that is provably hard against depth-3 circuits of this form. But nevertheless, let me present this depth reduction. So how do we prove lower bounds against a computational model? Usually we say that everything computable by this computational model has some structure, and here is a function that doesn't have the structure, hence a lower bound. Right, but we don't really understand circuits of formulas well. We are much better in working with low degree polynomials. Those we understand much better. So ideally, we'd like to say that everything computable by a small circuit can also be computed by something like low degree polynomial, and then would present a function that cannot be computed by a low degree polynomial and conclude a lower bound. But this approach doesn't really work because, say, the OR function has tiny formulas of linear size, but requires polynomials of highest degree of linear degree. So this simple approach doesn't really work. But when exact polynomials don't work, we use either randomized or probability or approximate versions of like whatever polynomials, and that's exactly what we're gonna do in this result. We can't say that whatever small formula computes has a low degree polynomial, because even the OR function is a counterexample, but we can say something similar with randomized and approximate versions of polynomials. So first, let me remind you what we mean by approximate and randomized polynomials in this case. If I have a function from n bits to 1 bit, then an approximate polynomial for this function is a polynomial over the reals. This is very important. This polynomial is over the reals that approximately computes this function f at every point. That is, for every input, the difference between this polynomial and the function is less than 1/3. So this polynomial p, it always tells apart zeros of f from ones of f. Just at 0, it can output maybe 1/3. At 1, it can output 2/3, but there is always a gap between them. Okay, so this is what approximate polynomials are. Now, and we'll use this beautiful result by Reichardt that says that every function from n bits to 1 bit can be that has a De Morgan formula of size s, can also be computed by an approximate polynomial of degree square root of s. Now, probabilistic polynomials. If I have a function again from n bits to 1 bit, then a probabilistic polynomial is a distribution of polynomials over f2 such that for every input, a random polynomial correctly computes the value of my function and this input with all but negligible probability. So probabilistic polynomials is a distribution of polynomials over f2 such that for every input, a random polynomial gives the correct answer with probability 1 minus epsilon. Okay? Approximate polynomials are over the reals, probabilistic polynomials are over f2. Now, the conjecture that we're going to be using, which we believe is plausible, is the following. Every De Morgan formula of size s has a probabilistic polynomial, that's polynomial over f2, of degree square root of s, with some constant error. And some reasons to think that this conjecture might hold are the following. Every De Morgan formula has approximate polynomials over the reals of this degree, of degree square root of s. Also, all symmetric functions do have probabilistic polynomials of degree square root of s. Also, all De Morgan formulas that are kind of layered, like and of ors of n's of ors of n's of ors, they do have probabilistic polynomials of degree square root of s. Those are the main reasons why we believe this may hold for all De Morgan formulas. And from now on, like, let's use this conjecture to prove our main result. Okay, so the main result for formulas is the following. Take a formula of size n to the 4 minus m epsilon 2 epsilon. We'll rewrite it as a sum of f2 polynomials. The sum has sub-exponential size, and those f2 polynomials have sublinear degree. Okay. So first of all, every formula is a tree, and trees can always be balanced in various nice ways. In particular, it is known that the De Morgan formula can also be balanced in the following way. So I can rewrite every De Morgan formula of size n to the 4 minus 2 epsilon as a top part of size square root of it, that is of size n to the 2 minus epsilon, and all bottom formulas, all small formulas, will be also of size square root of it, that is of size n to the 2 minus epsilon. Okay, so every formula of size n to the 4 minus 2 epsilon can be rewritten as a top formula of size n to the 2 minus epsilon of small formulas, each of the same size. All right, now I'll rewrite the top part of the formula as an approximate polynomial over the reals. By the result of Reichardt, this approximate polynomial has degree square root of s, that is n to the 1 minus epsilon over 2, or 1 minus epsilon. Okay, so a real polynomial of this degree means it's just sum of products. And the degree of each product is sublinear, n to the 1 minus epsilon over 2. Okay, and now we apply our conjecture to each blue formula, to each formula at the bottom. By our conjecture, each such formula has a probabilistic polynomial over f2 of degree square root of s. That is, it can be written as a parity of n's, each end of degree n to the 1 minus epsilon over 2. 1 minus epsilon, doesn't matter. All right, so at the top I have real polynomials of degree square root of s. In the bottom, I have f2 polynomials of degree square root of s2. Now I will hit the top real polynomial with a recent result of Shorstov, with robust polynomials. Robust polynomial says that if I have a real polynomial that takes inputs like zeros and ones, then I have another real polynomial of essentially same degree that even if the inputs are shifted by a little bit, by small constants, like every input is shifted by at most 1/3, this new polynomial of essentially same degree computes the correct result, computes whatever the original real polynomial computed. So it allows us to make little error in every input. I hit the top real polynomial with this robust polynomials result by Shorstov. And now for the bottom blue polynomials, I have probabilistic polynomials there. I have a distribution of f2 polynomials. Now I sample linear number of such polynomials and take the average of them. By some Chernoff bound, this tells me that every output will be wrong only with small constant probability, say like 1/3. So now by Chernoff, if I take average of a bunch of such polynomials, then the results are good enough for this robust polynomials, because each output here is wrong only by at most 1/3. So now in the top, I have sum of products. In the bottom, I have sum of parities of n's. Here is what I have: sum of products of sum of parities of n's. Now I'll apply the distributivity law to product of sums. I can always rewrite it as some huge sum of products. So here's what I have now. Now note that this product takes zeros or ones. Such a product is also known as end. If all the inputs are zeros or ones, I can rewrite it as a Boolean function end. Now, every Boolean function can be written in the Fourier basis. That is, it can always be written as a sum of parities. And that's exactly what I'm doing here. Instead of this end, I'll write sum of parities. Finally, I'll just collapse this sum of sum, and I'll collapse this mod of mod. This will give me sub-exponential sum of f2 polynomials of sublinear degree. That's exactly the result we wanted to prove. Under our conjecture, every De Morgan formula of size almost n to the 4 can be rewritten as a sub-exponential real sum of f2 polynomials of sublinear degree. All right, that finishes this proof. And in fact, this finishes my talk. I just wanted to end this talk with a slide with summary of what improvements of pseudo-random results are needed for new circuit lower bounds via variant or our frameworks. That's it, and thank you for watching this talk.